Electromagnetic induction is taught as a neat loop of wire and a magnet. The math is elegant, and the physical reaction is completely contained. But applying that principle to a national power grid involves routing tens of megawatts of active power. At that scale, the thermal and electromagnetic forces involved are volatile and destructive if uncontained. Look at the scale of a real-world grid transformer. This is a massive piece of industrial architecture, packed with dense cooling fins and thick insulating layers. Taking the physics of induction and safely encasing it in steel and oil requires uncompromising engineering parameters. Without a strict operational envelope, a theoretical transformer design is merely a recipe for grid failure under real-world loads. In India, that operational envelope is defined by IS 20261. This is the definitive standard for general power transformers, adapted directly from the international IEC 600761 blueprint, but calibrated specifically for regional environmental realities. This standard functions as a legally binding framework, defining environmental survival and physical architecture, rather than simply listing parts. To understand how this works, we need to build a conceptual transformer. We will establish its operating environment, categorize its physical windings, and calculate the standardized math that governs its output. Mastering the rules within IS 2026-1 marks the difference between sketching a functional schematic and deploying resilient national infrastructure. The standard begins by defining normal service conditions. This is the baseline reality required for a manufacturer to guarantee their hardware's rated specifications. We can visualize this as a strict environmental bounding box around the transformer. Every parameter inside this space is tightly controlled. First is altitude, capped at 1,000 meters above sea level, as thinner air reduces heat convection. Next are thermal limits. Ambient air must remain between -5 and +50 degrees Celsius. If the unit uses liquid cooling, the standard specifies that the inlet water cannot exceed 30 degrees Celsius. The limits then extend to the electrical environment. The transformer must be fed a symmetrical 3-phase supply voltage. Waveform purity is strictly enforced. The supply can have no more than 5% total harmonic content, and only 1% even harmonic content. Any distortion beyond this accelerates thermal runaway inside the core. If a grid operator breaches any single parameter in this environment, all subsequent engineering calculations, thermal projections, and manufacturer guarantees are immediately invalidated. Once the external environment is locked in, the standard dictates the internal physical architecture. Transformers fall into two primary physical categories. First is the dry type, where the magnetic circuit and copper windings are exposed to air. For grid-level applications, the standard pivots to the heavy-duty oil-immersed type. Here is a cross-section of an oil-immersed unit. To manage thermal stress, the core and windings are submerged in an insulating liquid. As the core heats up under load, the fluid expands into this oil preservation system at the top, accommodating the volume changes. This initial architectural choice dictates exactly which subsequent physical testing protocols, such as the temperature rise limits in IS 2026 Part 2, engineers must apply to the unit. Inside the tank, the copper coils themselves are governed by highly specific definitions.
For example, the terms primary and secondary only denote the direction of active power flow. When defining the physical hardware, engineers use high voltage and low voltage based on the rated potential of the winding itself. In an autotransformer, different voltage circuits share physical pathways. The standard defines the shared segment as the common winding, while the remaining portion is the series winding. If we alter the circuit to regulate voltage on a transmission line, the layout becomes a booster transformer. Here, an energizing winding supplies power to an independent series winding, allowing operators to shift the phase or alter the voltage mid-line. Transformers often require auxiliary features, like a delta-connected stabilizing winding. This winding is intentionally isolated and never connected to an external circuit. Its role is internal physics management, specifically decreasing the zero-sequence impedance during ground faults to protect the core. Adopting this standardized nomenclature allows manufacturers and purchasers to reach precise technical agreements on transformer function. By defining a winding's type and intended connection, engineers accurately calculate how the system will react to fault currents before the hardware is ever deployed. Once the physical coils are mapped, the standard assigns them nameplate ratings, the mathematical values assigned to the transformer's operation. The foundation is rated power, or SR. This is the conventional value of apparent power assigned to a specific winding. Next is rated voltage, or UR. This is the potential designed to be applied, or developed at no load, across that specific winding. Together, the rated power and rated voltage dictate the exact rated current, or IR, that will flow through the line terminals at full load. This is the standardized mathematical breakdown for a three-phase system. Rated current equals rated power divided by the square root of 3 times the rated voltage. The square root of 3 in the denominator is used to calculate phase-to-phase voltage for star-connected networks. For delta-connected single-phase banks, the line current itself is divided by the square root of 3. The math accommodates tapped windings, where operators can mechanically change the effective number of turns in steps to adjust the voltage ratio. To prevent mathematical ambiguity, the standard enforces a rigid rule. Every rated quantity on a spec sheet relates strictly to the principal tapping, unless specified otherwise. These standardized mathematical definitions ensure that a 50 megavolt ampere rating translates to the same physical output regardless of who manufactured the hardware. The power transformer functions as a system where environmental limits, physical architecture, and mathematical ratings are precisely interlocked. IS 2026-1 synthesizes these factors into a single, reliable entity. This operational substation unit illustrates the standard in practice. The size of the tank and the arrangement of the cooling fins are direct physical responses to the rated power and thermal limits established in the design phase. These foundational definitions provide the necessary baseline for physical stress testing. Once a transformer meets Part 1, it must undergo the thermal evaluations in Part 2 and the short circuit withstand tests detailed in Part 5. IS 2026-1 provides the engineering language required to build, scale, and protect a national power grid.